important in
This meeting is being recorded.
how hashing is used in other applications apart from blockchain in day-to-day computer science applications that we use every day, and also how it is important in blockchain also. So my name is Rishabh Chatterjee. I work for 3665 Technologies. I'm currently a software developer, and let's get started on it. So the first thing that comes in our mind is what is hashing. So the Wikipedia definition that we get when we search hashing is a hash is a mathematical function that converts an input of arbitrary length into an encrypted output of a fixed length. Thus, regardless of the original amount of data or file size involved, its unique hash will always be the same size. So there are some key points in this definition that we really need to consider. One is hash is a mathematical function. So by function we mean that we can uh, like see it as a black box. Like we really don't want to know what is it inside it, but what are the documentation or what is the function, like what does the black box do, like what input does can we feed into that black box and what output do we get. It's just that. So it is a mathematical function in which we can feed any data of arbitrary length, like data by mean we characters. It can be image, like binary data or any kind of data that is in characters, and we get a encrypted output of a fixed length, which means that the input data can be of any length and the output data can be will be always of a fixed length. Thus, regardless of the original amount of data of the file, the unique hash will always be of the same size. So this is the overview or a brief definition of what hash means. Just what hashing means for any data type, like any data. By hash, we mean this, like just converting that data into an encrypted output of a fixed length. Next comes, this is a hash table, like that we have, that we use in computer science. We may have heard of it. So what it does is there is a black box that we just mentioned right now. So this is a black box, and here are the data points, and these data points are mapped to these numbers. And when we feed this data point inside of it, we get a hash value, and in that hash value is a we store the phone number of these items. So if we know what arrays are, we can simply say that these are the index of the of these arrays. But let's say we don't know what arrays are. We just have a page, and each page has this page number, and we want to store phone numbers for some people. So we have names of the people and we have phone numbers for those people. So how do we store that efficiently so that we have a like we know the number and just go to that page and get the phone number for that person. So we can use hashing for that. So let's say I feed into that black box a name, and that name gives us a number. A number will be 1 to 100, representing the page numbers that we have inside a book, inside a notebook, and we store the number for that person inside that in that page. Let's say one page only has one person's phone number, just for simplicity for now. So John Smith, we feed into the data, feed into the black box, and it gives us number 2. So we go to page number 2 and enter the person's number in that. We say Lisa Smith, enter into the black box, it gives us a number 1. So we enter her phone number in page number 1. So let's say next another person comes in who doesn't know all this stuff, but they know the mechanism how to find the phone numbers. They have this function black box. See, they enter the number. They know that in page number 1, Lisa Smith's number will be available. As she enters this into the hash function, they will get 01 value. They can just go to 01 and fetch the phone number from there. So this is a simple application that we can use in hash functions. And this is what we call in computer science a hash table, which is used in a programming language. In every programming language there is a library called map function. In C++ we have map, in JavaScript we have set, standard set, these kind of stuff. So all these map functions is based on these basic principles, or this basic idea that we feed in a data input and we get a fixed length output. And also, if you notice in this hash table, there is also another point, which is one to one function. This is a particular property of a function that is one to one. By one to one we mean, let's say I enter John Smith, okay, and I get 02. So the one to one property states that John Smith will always get 02. It can't happen that one time it will get 02 and another time it will get 01 or 03 or 13. It can't happen like that. Every time I enter John Smith, I have to get 02. That only then will this property hold, or this whole logic will hold. Otherwise it will fail. Let's say John Smith gives us 01 and 02. A third, like, how will we know where to go and search the value? It is entered in 02, right? So a single input always points to a single output. Multiple outputs can't happen. And also, a single output will always, uh, the pre-image of that, or the input of that uh, value will always be 1. Like 02 cannot map to Lisa Smith or John Smith, as it is a one-to-one function. So this is a simple property. These are the properties that we have in hash table. To get in more depth into it, we can give properties of collision detection or how to manage collisions. Let's say John Smith and Lisa Smith, there are like 100 people in this hash table. Like, let's say there are only 100 pages in the notebook, then only we can enter 100 people in that notebook. More than that it can't hold, right? Because every person will have its own unique hash, like unique hash generated. And the on also another function is that John Smith and Lisa Smith, like any two names cannot have a same output that they can generate. That will not be a case. Like every output that gets generated will be unique for that particular input. So this was an example of hash table. So let's move on to some features that we discussed here, but let's note them down and like pinpoint them, that what we discussed here. So moving on, these are some features of cryptographic hash functions. So hash functions are what we discussed before. So cryptography is a branch of mathematics that deals with encryption of data, and the encryption and decryption using keys. There are many kinds of cryptographic hash functions. So where it uses cryptography in setting the function, like the black box which uses cryptography to get the output is called cryptographic hash functions. So some points for cryptographic hash functions are that we require or need in our application, especially blockchain application, are it shall be deterministic for of same inputs, or it shall be deterministic. Like, we know that if the same input, let's say I enter my name Rishabh, and it will always give me the same output, no matter how many times I enter the name. Like, let's say I enter ABC, it will give the same output no matter how many times I repeat the process. So for same inputs, the output will be deterministic. Like, I will know that this will be the output, no matter how many times I enter the same input, the output is not going to change. And it shall be time efficient. It means that we need to make many number of computations for these hash functions. Like repeated computations shall be made to check the validity of blocks. We'll come that to come to it later. So making these kind of computations, or checking, like getting a hash for a input, it should be time efficient, else our system will be very slow. So feature that we need in a good cryptographic hash function is time efficient. Like it should take a couple of milliseconds to calculate a hash for a big data. So that kind of time efficient we need. And another is infeasible to compute pre-image. We will see that, let's say I get an output for my name in a hash function, and it should not be possible to get the input that I provided to get that particular output. I can't like brute force 1 2 3 4 and get the output. Like let's say in the previous example we had this like 0 to 100 possibilities for entering the phone numbers for this particular person. So let's say I have a encrypted, like I have the output of 02 or 014. Let's say I have the output of 14 and I want to know which person does it belong to. Maybe I'm not authorized to get the value of user that has this phone number 14 mapped to it. Currently it's Sandra, but let's say we don't have it. So I will just compute the pre-image, like we have all the names, and let's say for John Smith, it's going to give us the same output, right? We have a list of names, and it's going to give us the same output. So let's say we brute force for all the given names that we have, and search that which name has number 14 in it. If we find that, we will match that value with the phone number. So that kind of this is not a very good cryptographic hash function that we have right here. It is just a basic one, but later on we will see that on good cryptographic hash functions that we use to secure our blockchain networks, it is not possible to compute the pre-image by just brute force, or it is not feasible. It is possible, but the amount of time that it takes is very long, like hundreds and thousands of years by brute forcing 256 bits of data one after another to find which was the output. Like output can be anything, right? Like it can be a random string of thousands of letters, and or it can be 01 or 02 or abc, but the hash value output that we get is always the same length. So it is in not any way possible to like compute all the possible inputs that we can provide. Moving on. So it was in, as we saw, it is infeasible to compute pre-image. And next we have change in input changes the output completely. So in SHA 256, which is a very common or widely used encryption algorithm, it gives us an output of 256 bits of encrypted value output that we get for any input. So let's say I enter ABC, we get a 256 bit of data back. And let's say I enter a long, like a poem or like a novel fiction, it will calculate the hash of that fiction novel and give us a value of 256 bits for both this like very different kind of input. And let's say even if I change a b c d, it will completely change the output that we get. Like we can't like guess or check, like we can't guess that what will be the output if I change an input by some degree or by some variable. We can't guess that. So this we can definitely say is a pretty secure feature. Also, it should be collision resistant. By collision resistant, we mean that every possible input, it has to be unique. Like ABC and ABCD, ABCDE, all these inputs, different kinds of inputs, should give us a unique hash. No two input hashes should collide or be same. It will be same at some point after we try to, like it says resistant, not impossible. Collision in like collision free, it doesn't state, it said resistant, because no cryptographic hash function currently developed is not collision free, but it is infeasible or very unlikely to collide. It is so unlikely that it is almost impossible. So we say collision resistant is also an important feature that we get. So examples of hash tables or hash functions that we always use are in our day-to-day life are text encoding, like we have must have heard ASCII, UTF-8, all those kinds of encodings that we use in, like we type in our computer and we type in English alphabets or any other alphabets, and the computer understands this. So they have a hash table inside of them with ASCII codes or UTF-8 encoding, which maps each alphabet or letter characters with a separate set of, like with a set of numbers. Like every A is 65, last uppercase A is 65 in ASCII or something like that. So every character has his map to a, like a unique unique number, and with that number is decoded to binary, and the computer is able to understand it. DNS file systems, like we have an IP to domain mapping that also uses hash functions in some way. Git commits, if we know Git, if we try to do any commit in Git and try to log that, we will see a graph type of a view, and each commit we get has a unique hash or an encryption unique hash code with it, like along with it, so that we can uniquely identify what commit was done by whom, like, and go to that commit. And some non-computer science examples that we saw was phone book one that I just gave, and dictionary that we all have, not entirely like a pure hash table, but it is somewhat like that. Like the basic philosophy of that is somewhat like that. So after discussing hash functions, let us go to a sample applications that exists in open source, and we can see how hash functions work by entering some value. So let's see that. So this is an example of SHA-256 hash. It, for example, it gives us a output of 64 bits. By 64 bits is, we mean that this output that we get is of 64 characters, like 1 2 3 4 characters, by that 64 characters. So let's say I enter my name here, RISAV. It gives us a hash that ends with 08E83. So every time that I enter this hash, this input, it will give us the same output of which ends with 08E83. So this is a property that we just saw, deterministic for same outputs. And let's say I change the input value by even a margin, like let's say I add a E at the end, it completely changes the hash function. It doesn't, like currently 8 is not present, and the up, like start also gets removed, and it just, like it's, we can't see or we can't guess which one was it. And we can also see that this is a very big, like 64-bit data, and we can't compute the pre-image, like what was the input that was provided for which this output we will get. We can't do that. So, and this is just a single line of text. So if we can enter also hi, so by this we can also have new lines and other stuff. But no matter how many characters or how many new line spaces or commas, any characters that we have, it will always give us this same 64-bit of hash function. It will compute, it will like feed this into a black box or a function, hash function basically. It will feed that into that hash function, this whole data value, and it will throw out a 64-bit string which will be unique and adhere to these properties that we have for hash function. And we can see this is also time efficient, that it takes very less time to compute these hashes. Okay, so this was hash in its like basic level. It was just how hash works. So next topic is how we can use hashing and its uses in blockchain. Like we how do we use block hashing in blockchain? So hashing is very fundamental in blockchain. Like it is very fundamental in blockchain. It is the core philosophy of cryptographic hash function and cryptography that we use in blockchain to verify and secure our blocks and to see that it is verified. And it is also the core logic of what miners do that we hear about, that miners mine stuff. So what is mining? They just like brute force a certain number. They try to find that number, and for that number, they want to find the target hash for that for that respective block. And if they find that block number and it matches, they would have mined that block. That block would be added to the chain, and they will get some rewards for it. So let's go to it one by one. So application of hash functions in blockchain. It is a very fundamental in managing blockchain. Miners try to verify the authenticity of a block by computing hashes mining. So what do we mean by that is, let's say we have a block. This is a single block. We won't like we are still not going to be diving to the blockchain part of it and the distributed stuff. This is first we covered hash in its like in its atomic level, and now we are covering blocks. So what and how hashes blocks use hashes to get the blocks verified. So there are three data points or four data points, if we may say, in this block. One is the block number, or second nonce, data, and hash. Inside this, the nonce is the most important number by which we try to verify the block. Let's say I enter my name here. I say hello world and my name in a new line. So this block contains this data. This is block number one, and all this data with this nonce gets computed. This nonce is basically getting added in the block header that we have, and with all these data, we produce a hash for it. Like this is the hash that we produce, and uh, what the miners want to do is get a nonce value which will produce a hash with starting four digits as zero. Like that is the target hash for this demo, but it may vary depending on blockchain to blockchain. Like different blockchains has have a target hash of different logic. Let's say the target hash would be less than equal to something, or it can follow different logic. For like the nonce, the target hash would be less than equal to some other value or any set value. They can uh, like use different set of logic to get the target hash. But here the target hash is, for a block to be verified, we want the hash of that block to have its starting four characters as zero. So if we hit mine, it will just go 1 2 3 4 to a nonce value that will give us that hash. So if I hit mine, it will just buffer, and for we find this nonce value. So if this nonce value, if we add in the data and block, we get a hash value which starts with four digits as zero. The the good and the like a very secure thing of this is, even if we change a single digit or a single character, let's say I add a space, I delete a letter, I like delete world, it will completely change the hash because the data is getting meshed, and this nonce no longer gives us the target hash. So again, we have to mine the block to make it verified. So this is what miners do basically. They keep on finding, like by brute forcing 1 2 3 4 5, for which number will we be getting the target block. Next number that we got is 86222. So it is a very time consuming process, and the more complex it is, the more time it takes to compute this target hash. So now it mined to this, and let's say I change it again, and it will again be non-verified. So this is the scenario of how hash is used, cryptographic hash functions, and the concept of target hash was introduced here. A hash was generated and a target hash. We just see that if the hash is equal to target hash, and this is how hashing was used in a block, in used in block. And next we will see that how this block is linked to one another, and how hash is also used there also. So going forward, we have a link of blocks, as we can see, and the blocks itself are pretty much similar that we saw before, but one added data point is the previous one. So previous means the hash that we compute for the previous block is also present in the next new block that we add. So currently there are 5 blocks that we have, and each block has a nonce value, and these all are verified blocks. These are all good and well and good. And let's say a very like a intrusion comes in this blockchain and tries to modify some data. So let's say I just modify here and I say hello. So you can see this is no longer a valid block, right? So because new data was added, this nonce no longer gives us a target hash of starting of 4 zeros. The previous, till the previous block is valid, but this current block is not valid. And also because this current block is not valid, the next block, as it contains the previous block's hash function, no longer is also valid. So a property that we derive from here is that if a certain block in a blockchain gets unverified, all the next blocks inside the blockchain starting from that block will also be unverified. So if I like edit this one, and if this gets unverified, this block and all its next blocks in the blockchain will also get unverified. So let's say we mine this. So will, if I mine this, will all these blocks get mined also? Like, will they also get automatically verified if we just mine this? So the answer is no. So let's say I make it unverified, the block number 1, which is the genesis block, and we find the nonce which gives us a target hash. But as we will see that it will not generate like it will not verify all the next blocks in the blockchain. Why it will be the case? Because the hash will be different, and all these hashes will be have to be different also for the previous blocks. And next, then we have to mine each one of them one after another to make the chain verified completely. So let's say I mine this one. It will produce a target hash of starting with 4 zeros. We get a nonce, and this hash also has to be replicated here. As it is a new hash, it will, we also have to mine this one. And same goes for this one and all the other ones. It will take some time, so let's just refresh the page. So the longer the blockchain is, the more difficult it is to make any changes, like for any people that are uh, not like not good people like hackers to make any changes inside the blockchain, as they have to change all the next blocks that arise after it. Now is it mining? Let's go to our slides. So, so to form the chain of blocks, hashes of previous verified block is also included in block header of the new block. As we saw that new blocks, block hashes are included in the previous block header. Next point is computed hashes needs to meet the criteria of a target hash. As we saw, the starting here, the target hash was a hash that starts with 4 zeros for the block to be verified. These mathematical notions with the concept of chaining and distributed system is what makes the blockchain work. So these are basic fundamental like building blocks of a blockchain network. With this, this was a concept of chaining that was introduced to a block with hashing involved. And the next topic that we will cover next is the distributed systems, or the next like with the distributed system and the chaining is how blockchain will work as it works now. So this was the session with how hashes is used in blockchain to verify and verify the process. So any questions till now?
No,
Any
I think
questions for the session?
it's a good session, Rishabh. What did you learn? Did you learn anything in the session? क्या बोलो? हाँ, बहुत कुछ. क्या जैसे? नोट बनाया. Okay. No, cool.
मेरे को बस इतना पता चला हैश मेक्स अ ब्लॉकचेन.
Hash makes a blockchain. अच्छा. Cool. Any questions from anyone? नहीं, बढ़िया. नहीं, but Rishabh, it was a good session. I enjoyed the session actually.
Thank you, sir.
Yeah. So thanks for that, Rishabh. I think great session, right? And
And Rahul and Sugato, you guys have no questions? You understood everything?
I think Sugato joined a little late, so he would have missed some parts
Almost. Okay,
of.
not bad. Okay, cool. All right, guys. Thank you. Thanks, everyone. Have a great rest of Sunday.
Sure.
Thank you.
Thanks,
Bye.
everyone. Thanks, Rishabh. Thanks a lot.
Thank you. Bye.
Bye.